Hello! This video begins a new sub-project of the DIY 8-bit computer series. It's going to take a bit of explaining, but I promise there will be actual technical content, including some interesting hardware. I'm very excited about this new project, and I think it will lead to some interesting content. So, before we get to the technical stuff, let me explain the idea behind this project, and also explain why I haven't actively been making videos for the past couple of years. When I started on the 8-bit computer project, it was super fun to work on, I was learning a ton, and I made steady progress towards my goal of a complete 8-bit computer system. Eventually, I reached the point where I needed a display, and that's where things got bogged down. In my original analysis, I identified two options for a display controller. One, an authentic retro display controller such as the TMS9918A, or two, an FPGA-based display controller. For several reasons, I thought that option 2 made more sense. VGA monitors are plentiful, cheap, and look great. The resolution would be much higher. The flexibility offered by an FPGA would allow me to create a display controller that prioritized the features I was most interested in, mainly text mode. I think this analysis was valid. What I didn't anticipate is how difficult it would be to work with FPGAs. The main problem is that it's quite difficult to know exactly what is going on inside the FPGA. You certainly can't monitor internal signals with an oscilloscope or a logic analyzer. I realize now that a proper FPGA workflow involves simulation, test benches, timing analysis, and potentially even formal validation. Someday, I hope to learn how to program FPGAs properly. But here's the real problem. I just don't find FPGAs to be fun. A huge part of why I got into digital electronics is because it involves building things, meaning real, tangible things. I love building circuits on breadboards. I love building circuits on protoboards with lots of point-to-point soldering. I love designing and assembling PCBs. I love debugging circuits using a multimeter or oscilloscope. For me, FPGAs don't really offer these experiences. I have experimented with option 1 using a retro display controller, and I will likely be making a video about a combined TMS9918A/YM2149F board in the near future. However, I don't really like the arcane programming model and terrible image quality of this era of devices. From a practical standpoint, even just finding a way of displaying a video signal produced by one of these devices is inconvenient and often expensive. So, for the last year or so, I felt unmotivated to push further on either of these options, and that brings us to where we are now. But what if there was a third option? What if there was a path towards a display controller that would output standard VGA, would provide a high-resolution text mode with colors, and a simple programming model? What if this approach was actually fun to work on? A few months ago, I was reading Hacker News, and there was a link to the WireWrap Odyssey project. I will link to the website in the video description. You should definitely check it out. It's an incredibly inspiring project, a full 8-bit computer system built with logic chips. What caught my attention was the display controller, which generates a VGA text mode using logic chips. This is an idea that honestly had never occurred to me. I started thinking about whether I might be able to do something similar. Before too long, I was convinced that building a VGA text display from logic chips would be a lot of fun. I would be working with hardware rather than editing HDL code in a text editor. I would be able to probe internal signals using my oscilloscope. If I used a modular design approach, I could build and test it incrementally. Of course, there are some important challenges associated with building a display controller using discrete logic. I've thought about these challenges, and I think I have ways to address them. Challenge number 1, hardware complexity. A display controller will require a fair amount of logic to implement. A design could need large numbers of logic chips. Fortunately, there is an easy way to cheat: programmable logic. But wait, you say, I thought you said you didn't like programmable logic. Well, actually, there is one category of programmable logic device that I'm quite fond of: the humble GAL. A GAL 22V10 can easily replace a handful of discrete chips. I have a reasonable amount of experience working with GALs. They are fairly easy to find used on eBay, and Atmel even has compatible parts still in production. They can be programmed with the ubiquitous TL8662+ and T48 programmers. They are fast enough to work at clock frequencies needed for VGA. They have actual input and output pins you can probe. Because a GAL is reprogrammable, you can fix hardware bugs by popping it out, reprogramming it, and popping it back in. Challenge number 2, design complexity. A text display controller has a fair amount of complexity. The dot clock for 640 by 480 VGA is 25.175 MHz. That means that during visible regions of scan lines, the hardware must yield a pixel about every 39.7 nanoseconds. The sequencing of operations needed to fetch characters and attributes from video memory will be fairly intricate. It will be vital to have confidence that the design of a module is correct before building it as hardware. I think the way to address this challenge will be simulation. Specifically, Logisim Evolution is a powerful open-source logic simulator that will allow me to try out my design ideas before building the actual hardware. Logisim has models of a fairly large number of 74 series logic ICs, and I will also be able to build models of the logic that I will be programming into GAL chips, so I think I will be able to prove significant parts of the design in Logisim before building the hardware. Challenge number 3, high frequency. As I mentioned, the display controller will need to be clocked at 25.175 MHz if we want to generate full 640 by 480 VGA output. This is much faster than any digital circuit I've worked with previously. At best, the 74HC and 74HCT logic families are marginal at this frequency and, at worst, unreliable. I also lack experience in circuit design and construction at these higher frequencies. Fortunately, higher speed logic families exist. In particular, the 74ACT logic family is good up to about 125 MHz, so 25.175 MHz is easily within its design parameters. Also, because GALs are fast enough to work at this frequency, any part I can't easily source from the 74ACT family can be substituted with a custom-programmed GAL. The circuit design and construction issues are still an open question to some extent. However, as you will see in this video, I've already had success with several speed-critical parts of the design, so I think this problem will be manageable. Challenge number 4, video memory. A critical problem in a display controller is how to share video memory with the host system. The display controller must be able to read character and attribute data while visible lines are being generated. The host system must be able to write data to the video memory and, ideally, be able to read it back out. With standard RAM devices, some time-sharing scheme is needed, significantly increasing the hardware complexity and possibly reducing the system performance. The easy solution to this problem is to use dual-ported RAM for the video memory. With dual-ported RAM, the display controller can be reading from video memory at the same time that the host system is reading or writing video memory. My current thought is to use two IDT7134 chips, which would give me 8 kilobytes of video memory. My 8-bit computer system has 4 kilobytes of addresses reserved for I/O. A small part of this region is used for peripheral devices. However, the upper 2 kilobytes could easily be used as a window for the VRAM. Then we would just need a writable register to choose which 2 kilobyte bank the host system wants to access. Challenge number 5, rendering pipeline. A critical problem in the display controller is reading the character and attribute information from VRAM and delivering them to the rasterization hardware at the time they are needed to allow pixel generation. I think this will be the most difficult part of the design. However, it boils down to fetching one character value and one attribute value from video memory for each block of 8 pixels. As long as this happens just before the pixel output logic needs the rasterized pixel data, the hardware will work. We have 4 clock cycles per byte fetched from VRAM, meaning about 158.8 nanoseconds for each byte. The dual-port memory chips have an access time of 70 nanoseconds or faster, so this timing should be feasible. The interesting challenge will be to generate the control signals. Challenge number 6, physical size. If you've seen previous videos in the 8-bit computer series, then you may be aware that I'm building my 8-bit computer system as cards connected to a passive backplane. The cards are 15 centimeters by 9 centimeters, and there are only so many DIP ICs that you can fit on a card of this size. It's a distinct possibility that even if I get a design working, it won't actually fit on a standard card, at least if I use through-hole ICs. One workaround for this issue would be to use surface mount parts. You can fit a fairly large number of SOIC parts in 135 square centimeters. The GALs and dual-port RAM chips will probably still be through-hole, but I think there's a possibility that I can find a way to make everything fit if all of the other parts are SMD. Challenge number 7, time and effort. At the time I'm making this video, in May 2024, my spring semester is done. During the summer, I won't be working on any accreditation self-studies, looking at you, ABET, and as far as I know, Nintendo isn't planning on releasing any new Zelda games or DLC. So, I think I will be able to devote some significant time to this project over the summer. It remains to be seen how much progress I will make, but if I knew what I was doing, it wouldn't be as much fun. I guess we'll see how it goes. Alright, let's get to work. In this video, my goal is to generate the horizontal and vertical sync signals for 640 by 480 VGA. We will also compute visibility information to distinguish between pixels that are in the visible area of the frame and pixels that aren't visible. This should get us to the point where we can display a screen with a solid background or foreground color. I realize that this might not seem too exciting. However, the horizontal and vertical counters needed to generate the sync signals can also be used to provide timing signals to the more interesting parts of the design, such as the memory fetcher and the rasterizer. Alright, so here's the outline for the rest of the video. I'll talk a bit about sync signals and how they should be generated, and that will inform the design of the actual hardware to generate them. I will show you a simulation in Logisim Evolution for both the horizontal and vertical sync generation, and that obviously is going to correspond very closely to the actual hardware that we are going to build. I'll talk about GALs and how they work. They're pretty simple, but they're very powerful. I'll show you the HCount, horizontal count module, and that was the first one I worked on, and I'll show you my little test setup and how I gained confidence that it was working correctly. And then I'll show you the sort of full implementation of what I have. There is a carrier board, there is a vertical count module, a sync module, and an output module, and then finally I'll show the entire setup working, displaying an image on a VGA monitor. Alright, so here is a schematic diagram of a 640 by 480 VGA signal, and this rectangle here is the visible region of the output signal, basically 640 columns of pixels, 480 rows of pixels. And obviously we'll need to generate color information for the visible pixels, and I'll talk about that a little later. For now, let's talk about how we can generate the synchronization pulses, both horizontal and vertical. So the way that VGA monitors originally worked was that they were CRTs, and there was an electron beam that traced out the pixels of the image onto the visible part of the screen, and these sort of extra non-visible parts of the signal were to allow the beam to, when it reached the end of one line, some time to get back to the beginning of the next line. And obviously on an LCD monitor you don't really have that, but the signal is still defined in this way. So the parts that are important for us are to generate a synchronization pulse in a particular part of the non-visible part of each scan line, and also the non-visible part of the vertical overscan area. So the numbers that I've annotated here are the pixel numbers for beginning of the visible part of the image, horizontal, end of the horizontal line, and then these 655 and 751 numbers, those are the precise pixel numbers in the non-visible part of the horizontal scan line where we need to generate a synchronization pulse. Alright, I've added 799 here. That is the last pixel in a scan line, and it immediately precedes the first pixel in the next scan line. Alright, so 640 by 480 VGA has negative sync pulses, and so basically when we generate the horizontal sync signal, we need to let it be high until the beginning of the sync pulse, at which point it goes low and remains low until the end of the sync point, and then becomes high again. And when the monitor sees the sync pulse, it then knows precisely how the overall horizontal scan line is aligned so that the monitor can just display the visible pixels in that scan line. In a similar way, the display controller will need to generate a vertical sync signal, and again, there are particular scan line numbers that mark obviously the visible region, the vertical visible region, but then the beginning of the vertical sync pulse, the end of the vertical sync pulse, and those happen at lines 489 and 491. And similarly, the VSync signal for this particular video mode is normally high, so we leave it high until the beginning of the vertical sync pulse, and then it goes low until the end of the vertical sync pulse, in which case it becomes high again until the end of the frame, which happens at line 524. And immediately after this last non-visible pixel, then the beginning of the next frame begins, and we start over at the beginning of the visible frame. Okay, so in terms of how we will actually implement the generation of these horizontal and vertical sync signals in hardware, the most straightforward way to do it is to use counters. So we'll have a horizontal counter which basically counts which pixel in the current scan line is being generated, and that way we can detect when the begin horizontal pulse count and the end horizontal pulse count are reached. We can then manage the generation of that synchronization pulse. Similarly, in the vertical direction, when we reach the particular begin vertical pulse scan line and the end vertical pulse scan line, again, we initiate and terminate the generation of the vertical sync pulse. Okay, so now let's go ahead and look at our simulation in Logisim Evolution, and it basically does exactly what I just described, has two counters, horizontal and vertical, and manages the generation of the synchronization pulses based on the contents of those counters. All right, one thing I wanted to mention really quickly before we look at the simulation is that these counts for the beginning and end of the sync pulse generation, these are actually the counter values that should be present just before the generation of the pulse or the termination of the pulse, because the idea is that the sync pulse is going to be generated by clocking values into a D-type flip-flop, and so these are the count values that will produce the data that will be clocked in on the next clock edge, and thus they lead the timing of the sync pulse by exactly one clock cycle, if that makes sense. And we'll see that in the hardware design in just a moment. All right, and just for completeness, the same type of situation is happening here with the vertical sync pulse. These are the vertical counts that need to be present at the end of the scan line just before the beginning and end of the vertical pulse. Okay, all right, let's look at the simulation. All right, so here is the simulation in Logisim, and there's a clock signal and a reset signal, and then the horizontal count module, the vertical count module, and the sync generation module. I have some hex displays hooked up to the horizontal count and the vertical count, and some LEDs hooked up to the outputs of the sync module, and basically that lets me see the values as they change and verify that the signals are generated correctly. All right, so the first thing we'll do here is I'll show how to start the simulation, and basically what we need to do is generate a reset, and the design is completely synchronous, so basically no state changes except on a clock edge. All right, so the hand tool here in Logisim allows us to poke things like this reset signal and this clock signal. So reset is currently driven low, so that means the system is in reset. I'll provide one positive clock edge and then drive the clock low again. At this point, the system is reset. So you'll notice that the initial horizontal count is 0, but the initial vertical count is actually not 0. I've actually set it up so that the initial vertical count is the scan line on which the VSync pulse will be initiated, so that when the horizontal counter reaches its terminal value, we will begin the generation of the VSync pulse. And this was part of my debugging strategy, just to know that the timing of the sync signals was correct. All right, so now let me actually run the simulation, and what I'll show you here is pretty much how I use the simulator to validate the hardware design. So what I'm going to do here is I'm going to show the vertical sync pulse being generated, and as I mentioned, the initial vertical count value is the precise scan line at the end of which we begin the generation of the VSync pulse. So what I'll do is I'll run the simulation and let the horizontal counter get close to the terminal value, and then just before it reaches there, I'll turn off the auto clock and manually generate enough clock pulses to make it roll over, and you will basically see the VSync out signal here go from high to low, meaning the beginning of the VSync pulse. So as the HCount, the horizontal count, is incrementing, you will see the HSync out value go from high to low and then low to high. That is indeed the generation of the HSync pulse. All right, so let me set up the auto increment and run, and you should see these things happening. All right, so we are not in reset, so let me set the auto tick frequency. Let's set it to 32 hertz. All right, so that should only require a few seconds to get to the maximum horizontal count. All right, so let's start auto clock. All right, so you can see the horizontal counter counting up. let's see. Okay, so I'll probably fast forward this, but when it gets close to 31F, I'm going to turn off auto increment. All right, so we're approaching 28F, so you should see the horizontal sync pulse start soon. There it goes. All right, horizontal sync is done. All right, I've stopped auto increment. So let me generate some manual clock pulses. And essentially when the horizontal counter gets to 31F, that's the last HCount value. That's the very, very end of the horizontal scan line. The next clock pulse will reset it back to 0, increment the vertical count, and begin the generation of the vertical sync pulse. So VSync out will go from high to low. All right, so let's generate some clock pulses here. All right, so now HCount is at its terminal value, and you'll notice that this HCount module is now producing a high output on this HCount N output, and that, of course, is being fed into this sync module. All right, so the very next clock pulse, you should see VSync out go from high to low. Yes, on the next edge. All right, so that now we are in the beginning of the vertical sync pulse. All right, so now let me show you a little bit of the hardware, including the HCount module. The VCount module is quite similar, and then I'll talk a little bit about the sync module briefly. All right, so let's take a look at the HCount module here. So the HCount module, horizontal count, consists at its core of 3 74163 4-bit synchronous binary counters. There are a couple useful features of the 163 that are helpful for our application. One is that it supports parallel load, so you can present initial data to be loaded into the counter. We don't use that for the horizontal count, but we do use that for the vertical count for reasons I'll discuss in a little bit. The other useful feature is that there are enable inputs, and if they're both high, then when a positive clock edge arrives, then the counter does count up by 1, but if either of them is low, then no counting happens, and this provides an easy way to cascade these counters, and the idea is that there's a terminal count output that's high when all of the bits are set to 1, meaning it's at count 15, so it's about to roll over. That feeds in then to the enable or enables of the next device and tells it that it can count up by 1 because the previous counter is at its terminal count. And this provides a straightforward way to cascade these. It's better than doing a ripple counter because the problem with the ripple counter is that the higher, more significant bits get sort of progressively more delayed the more you add, whereas this is a design where it will count up fast regardless of how many devices are cascaded. So anyway, we take these free 4-bit counters. We're effectively using them as a single 10-bit counter, which is enough precision and resolution for the number of pixels that we have in one scan line. All right, let's talk now about this HCount control module. All right, so very briefly, the HCount control module, this is going to be one of our GAL devices, and its job is simply to look at the current count value and the current value of the reset signal, and then generate these particular combinational outputs. And essentially all it's doing is it's looking at reset and HCount, and then if, for example, if HCount is a particular value, one of these specific horizontal pixel count values that has to do with either the end of the visible scan line or the begin or end of the HSync pulse, it outputs on one of its outputs an appropriate signal. So for example, begin pulse, that is output when we reach the horizontal pixel that corresponds to the beginning of the HSync pulse. End pulse turns to 1 when we reach the pixel that corresponds to the end of the HSync pulse. HCount end, that's the end of the scan line, the very last pixel in the scan line. HVisibility end, that's when we reach the pixel that is at the very end of the visible part of a scan line. And then finally, this HC clear, horizontal count clear, that gets asserted either if we are at the end of the horizontal count or if reset is asserted. So either of those conditions will clear the count value and begin a new scan line. All right, so let's look quickly at the HCount control module. So the HCount comes in, the reset signal value comes in, and it's basically just combinational logic, AND gates, OR gates, and inverters. The idea is pretty simple. We use this giant AND gate, potentially with some inverters, to detect a specific combination of HCount bits, basically is the count at a point which is exactly equal to one of our special values. Some of the outputs of these AND gates get fed into an OR gate, and that will make a lot of sense when we look at how GALs work. So the way that the logic gates are arranged here is intended to be something that can be realized as a GAL, but otherwise nothing too exciting or interesting or surprising is going on here. We're basically just detecting particular HCount values and setting an output to logic high when a particular HCount is recognized. And the only one that isn't entirely based on the count is the counter clear signal, which simply looks to see have we reached the end of the horizontal scan line, or is reset being asserted. And if either of those is true, then we assert this active high clear signal. All right, so here is the vertical count module. It's very similar to the horizontal count module, and again, it's 3 7 4 1 6 3 counters. A couple of additional features that the vertical count module has. One is it takes the horizontal count end signal because you only increment the vertical count at the very end of a scan line, so that way we can detect whether we're at the end of the scan line and control the vertical count counters appropriately. The other thing is that we allow an initial vertical count to be specified, and the reason I think that will be useful is that when the hardware comes out of reset, I want it to be past the end of the visible part of the frame vertically to allow the hardware to have some time to initialize itself, and in particular get ready to start fetching data values from video memory before it generates the pixels in the first visible frame. So as we'll see, the actual hardware has a 10 position dip switch that will allow us to set this. Other than that, it's a very similar design to HCount. There is a VCount control module here. Again, that will be a GAL device. And again, it's just some combinational logic that looks at VCount, looks at the HCount end signal, and produces some outputs having to do with when the vertical sync pulses should be generated, when the vertical count counters should be reset, when we've reached the end of the frame vertically, and when we've reached the end of the visible part of the frame vertically. All right, and finally here is the sync module. This will again be realized as a GAL device. However, it is a little different than the horizontal count control and vertical count control GALs because it has registered outputs, meaning that the outputs are from a D-type flip-flop. So in the interest of time, I'm not going to go into great detail about how this design works, but the basic idea is that for generating HSync and VSync, in general, you want to feed back the output of this flip-flop back into its own input so that most of the time, the next output is just going to be whatever the most recent output was, so that, if the sync signal is high, it will in general stay high. But the factors that influence the output of the flip-flop to change are when a sync pulse is either beginning or ending. So it's pretty straightforward. Once again, you'll notice that we have these inverters and AND gates and OR gates. Again, the only real difference between the HCount control and VCount control modules is the presence of these D-type flip-flops. Again, that is going to have to do with the capabilities of a GAL. So let's go ahead and talk about how GALs work. All right, so here is the GAL 22v10 datasheet. So let's talk about the very high-level features. There are a total of 12 input pins. If you have any registered outputs, meaning you have a D-type flip-flop on an output, pin 1 must be the clock input that controls when data is latched into the output registers. And then there are a total of 10 I/O pins, so these can be either outputs or inputs. And each I/O pin over here is associated with a macro cell, and that includes the D-type flip-flop, tri-state output control, and an optional inversion of the output. So the most important thing here is this programmable AND array, and that is the connection fabric that connects the input and I/O pins to each other. So let's talk about how that works. All right, so here's the most important diagram in the data sheet because it explains how the I/O pins, the input and I/O pins, are connected to each other. And it's basically this grid where there are vertical lines and horizontal lines. So each vertical line represents either the negated or non-negated form of one of the I/O pins, and each vertical line can connect to any or potentially all of the horizontal lines. each of the horizontal lines represents a product term, and what each product term does is that it computes the logical AND of some arbitrary set of I or IO pin values. So in other words, each of these product terms is the logical AND of some subset of input and or output pin values. All right, so let's focus on one particular IO pin, this one, number 21, and its corresponding macro cell. And the main thing to observe here is that you can see it just barely here. There is an OR gate associated with the macro cell, and its inputs are a set of product terms. And as we've noted, each product term is the AND of some arbitrary set of IO pin values. And so effectively, this data value that gets clocked in or presented to the input of the macro cell at any given time is the logical OR of some set of product terms, each of which is the logical AND of an arbitrary collection of IO pins. And so this gives you a lot of flexibility in determining how to feed a computed binary input value into the macro cell at any given point. So what this means is that the Boolean value that's computed as the input to a macro cell is a sum of products, which you can also think of as a logical expression in disjunctive normal form. So for example, the output Q is assigned A and not B, that's one product term, or not A and C, another product term. And the different macro cells can have different numbers of product terms. So this particular one that we've highlighted can have 12 product terms, and the other macro cells have varying numbers of product terms. So if you recall your propositional logic, any Boolean function can be expressed in disjunctive normal form. So essentially what that means is that these macro cells can compute any Boolean function over all of the IO values that are in play. So that gives you quite a bit of power. Right, editing Dave jumping in real quick here. Because there are a limited number of product terms to each macro cell, you can't necessarily compute an arbitrary function of all of the IO pin values, but you can certainly do a lot. So we'll see how I've used the GAL devices in the various parts of the sync generation hardware in a moment, but hopefully that gives you a good sense of the basic capabilities of a GAL device. All right, so here's one of the logic equation files. This is specifically for the HCount control module. The GAL programming software that I'm using is called GALAsm. I'll provide a link to that in the video description, but it's pretty simple. You tell it what kind of device you're programming, you give it pin names for all of the pins, and then you have your logic equations. And this should make a lot of sense now that we know how GALs work internally, that each output is computed as a sum of product terms. This is pretty simple because it's just combinational logic. If we look at the design for the sync GAL, it's a little bit more interesting because there are registered outputs. So if you use a .r on an output, it means it's a registered output, meaning there's a D-type flip-flop, and that is subject to a clock signal. So the first input has to be a clock signal in that case. So pretty straightforward. All right, so now let me briefly show you the process for compiling a set of logic equations into a binary fuse map for the GAL device, and then we'll look at how we actually program the device. All right, let's say we want to compile our logic design and program it into a GAL chip. So here, let me do it for this sync.pld for our sync module. So we simply invoke GALAsm on the PLD file containing the logic equations. That will create a file with a .jed file extension that contains the fuse map, the ones and zeros that tell the GAL programmer software which connections to make between the horizontal and vertical lines. All right, so the software I'm going to use to do the programming is the open source minipro software. So let's see, our device is a GAL 22V10B. I want to write sync.jed. So let me put the chip in the programmer. All right, and then minipro does its work. It should only take a couple seconds. And there we go. So now our GAL is programmed with our custom logic, and it's ready to be put into the actual circuit. All right, so at this point, I think we're ready to look at the actual hardware. So here's the horizontal count module. So 3 counters, 1 gal. Constructed it on a small proto board using point-to-point wiring. Pretty standard. I think I made this one a little bit too cramped, so you'll notice the other modules have a little bit more room on them. Okay, so let me show you how I initially tested this particular module. All right, so here's everything set up on the bench, and on these pin headers are the horizontal timing signals that are generated by the HCount module. So there are the visibility end signal, the sync pulse end signal, sync pulse begin, and horizontal count end signals. So all of those should be pulses that go high for 1 clock cycle per scan line, and so the frequency of those signals should be the horizontal frequency rate. All right, so let us look at the horizontal visibility end signal. And so what you can see on the scope trace here is that the frequency of the signal is 31.46, etc. kilohertz, so that's exactly right, and we're getting a nice clean pulse. And the horizontal time base is 50 nanoseconds per division, so this is about 37 nanoseconds, which is exactly right. So this signal looks good. The other signals are going to look the same because they are at the same frequency. They're high for 1 cycle per scan line. All right, so this is how I got confidence that the horizontal count module was working correctly. So this is with 7.4 ACT counter chips. Let me show you what it looks like if I use 7.4 HCT counter chips. All right, well, here's something fun. I was looking for the 7.4 HCT 163 chips that I used originally in this module that didn't work correctly, and it turns out they were 7.4 HC13T. And in fact, it's not surprising that they didn't work because one of the idiosyncrasies of GAL devices is that their output high is actually quite low. It's only at TTL level, and it definitely can't drive 7.4 HC input. So in that sense, it's not surprising that the module didn't work with 7.4 HC163 counters. So I have put some decoupling caps on proper 7.4 HCT163 counters, and now I'm wondering if it's going to work perfectly. So let's see what happens. Okay, so as it turns out, the 7.4 HCT chips don't work either. So here I'm probing the visibility end signal, and as you can see on the scope trace, just getting nothing. So it's not surprising that these chips don't work at this frequency. It's really, at best, marginal at frequencies this high. So in any case, the ACT chips work great, and we do have confidence that the HCount module is working correctly. All right, so obviously we have multiple modules, and the way I am prototyping the entire design is that the modules plug into this carrier board, and this is just an IC pattern proto board that I've added single row pin header connectors to. So the HCount module goes here, VCount goes here. This is the output module, which I'll talk about in a little bit. This is the sync module, and this header here is for providing color information, and this will eventually hook up to the part of the design that produces the pixel data, and it has just enough connections now that we can send solid colors to the output module. And of course I have my oscillator module here that provides the 25.175 megahertz dot clock that we need. I've wired the connections between the modules as necessary, mostly on the top of the board, but some of them on the bottom of the board. This tact switch here is a reset signal, and nothing too surprising there. So let me talk about the output module a little bit, and then I'll hook everything up and we'll see a video signal on a VGA monitor. So just to show you the other modules briefly, here's the vertical count module, and it's very much like the horizontal count module, except that there is a 10 position dip switch that allows me to set the initial vertical count, and it also generates 4 low count bits to make them available to other modules. That eventually will be necessary for rasterization of the characters, and again, just point-to-point soldering on a proto board. Here is the sync module. The sync module is just a single GAL device, and it's basically just a straight line connections to bring the pins of the GAL out to header pins. Okay, so here's the schematic for the output module. So this is the module that actually produces the output signals that are sent to the monitor, the sync signals, the RGB color signals. So the signals coming into the module are a background color 4 bits, a foreground color 4 bits. So the color model for both the foreground and background is red, green, blue, and then an intensity bit. And if the intensity bit is 1, it boosts all of the RGB signals a little bit. So this is very similar to how color worked on the IBM PC in, for example, CGA text mode. And then 2 additional signals that come in are pix in. So this is the pixel input, 0 for background, 1 for foreground. And then an active low visibility signal. So if that is asserted, meaning low, it means that a pixel is visible. Otherwise, it means that we are in the non-visible part of the frame. So the reason the visibility signal is important is that it is essential to output the color black anytime that the raster is not in the visible part of the frame. And the problem is if you generate non-zero voltages on the color outputs, some monitors will misinterpret that as a sync signal. So for example, it's somewhat common to have monitors that will sync on green. And so if you're outputting color signals which have nothing to do with the sync pulses, then the monitor can't sync to your video signal. Okay, so the way that the hardware works is here at the end there is a 74ACT574, just a standard 8-bit register that is synchronous. So when there is a positive clock edge, the data present on the inputs is stored in 8 D-type flip-flops and then appears on the outputs. So the signals that are feeding into the inputs of this register are the selected color, either foreground or background, and then also the generated HCount and VCount signals from the sync module, and of course our clock signal, because everything in this design is synchronous. So the other 2 chips here are 74ACT157 quad 2-to-1 multiplexers. And so the first one, its job is to take the background and foreground color signals, 4 bits each, and then select which one should be sent on depending on whether the value of pix in is 0 or 1. So 0 selects the background color, 1 selects the foreground color. The other multiplexer selects between the selected foreground or background color and nothing, meaning all of the inputs tied to ground, meaning everything is 0, depending on whether the visible signal is asserted or not. So if it is asserted, then we select the actual colors. If it's not asserted, then we select all zeros, meaning that we'll send a black to the output register. Okay, the last thing to explain is how the RGBI digital values get translated into the analog color signals that are necessary to send to the monitor. And basically there's a little resistor DAC here that does that conversion from the 5-volt RGBI signals to the 0 to 0.7 volt color signals that the VGA monitor expects. And I've designed the DAC so that 2/3 of the voltage is contributed by the red or green or blue signal, depending on which color output is generated. And then if the intensity bit is set, that adds an additional 1/3 of 0.7 volts to reach 0.7 volts for that color output. So essentially it makes the overall color brighter, but also a little less saturated. Again, this is quite similar to how things worked on the IBM CGA and VGA text modes. All right, so here's the actual hardware for the output module. For whatever reason, I decided to go vertical on this one. I think because I didn't have any smaller proto boards, so I wanted it to be narrow, so I just made it a little bit tall. And here are the signals that connect to the carrier board. These are the signals that go out to the VGA monitor. Let's see, so we have our multiplexer, output register, and then here's the resistor DAC. Again, just point-to-point wiring. This wasn't very crowded, so it was pretty easy to do. All right, I think we are finally ready to see everything in action. So let me get everything set up and connected to a monitor, and I'll meet you back then. All right, so here is our test setup. I've got all the modules installed on the carrier board. What I have hooked up to the color input and pixel input signals is just this little set of dip switches on a breadboard, and so I can adjust these to be 1 or 0 depending on whether I want to send a 1 or 0 to the output board. All right, so up here we have an 8-inch eYoYo 4x3 1024x768 LCD monitor. I think it's similar to the one that Adrian Black reviewed a couple years ago. So these are really nice little monitors because they can accept all kinds of video signals, including VGA, and I have it mounted on a shelf above my workbench, so it means I can test VGA outputs without having to actually set up an actual monitor because there's one always available. All right, so let me go ahead and turn on the bench power supply. Okay, so you notice that we now have black, which is correct because all of the dip switches are set to 0. I'm going to turn on the red in the background colors, and so the pixel input is currently 0, so we should see a red background, and there it is. So let me set the blue bit on the foreground color, and so now if I switch the pixel input from background to foreground, now suddenly we're displaying blue, the foreground color. Let me turn on the intensity bit here so we now have a lighter blue. Let me turn, I don't know, red, so now we get a light magenta shade. So yes, everything works at this point, at least the parts of the hardware that are actually implemented. The monitor, locks on to the video signal, no problem. So I am very pleased by this result. I think this gives us a good basis for continuing with the design. Okay, well, thank you for bearing with me if you've made it this far, and here are my conclusions. So the sync and the pixel output both seem to work great. Overall, I feel like this approach is feasible. We didn't really run into any significant issues, and I'm cautiously optimistic. The next thing I'm planning to work on is VRAM, so I'm going to interface that to the host side, and of course, the host being able to put data into VRAM means that our rasterization hardware can get data out of the VRAM, and then that's basically it, but it'll be interesting to see how we get there. As always, I've got a link to the GitHub that has schematics and other info in the video description. So that's it for this one, and I will see you in the next video.